Oh, this, oh, over here? Okay. Yeah, there is, but it's not, there are two different colors. So there's pink and then there's black. The black is what's actually being shown as the graph itself. The pink is just describing what's going on. So they're illustrating with the pink as to what you should be thinking. So for the range, they're showing, hey, think about the top and the bottom. And just to make it easier on your brains, instead of just putting a brace and saying, okay, think about top, bottom, they always do dotted lines to draw your attention to a certain location. So it's more them just kind of being like, hey, by the way, the very top of it, follow it over, is, and the very bottom of it is. So the dotted line, same thing down here, how left, how right, and they just do the dotted lines to say this is what we're talking about. This is the left, this is the right, this is the bottom, this is the top. Yeah, so that's their way of like trying to go into the graph, but show you this isn't part of the graph. This is just us explaining to you where things are going on. Yeah. Any other questions about the example? Okay. So then let's go ahead and move on to finding zeros. Because finding zeros forces us to practice factoring. But first of all, before it forces us to practice factoring, over here, just in general, what are we doing when we find the zeros of a function? Oh, intercepts, x and y. No. The special name zeros of a function. Remember in calculator worksheet number 2? Some of you got confused when it mentioned something about when or where does the function have the value of, and we had to talk about that. So when we're talking about the function having a value of, are those x's or are those y's? Function values, f of x values from yesterday when we did function notation. Function values or f of x values are always y's. So when it's zeros of a function zeros, that's when only the y's are 0. And every time the y's are 0, the x-intercepts are what occur. So if you hear zeros of a function, it's not talking about, oh, set whoever you want equal to 0. It's specifically saying the y equals 0 or the x-intercepts. I want you guys to go ahead and write at some location around here. I want you to write the word factor. I want you to get out a colored pen. I want you to highlight. I want you to circle. I want you to do something that reminds you whenever we're trying to find the zeros of a function, always try to think of factoring. Always try to think of factoring. Sorry, I had a flat tire this morning, still kind of playing catch up. But I got in the classroom by 8:05. Wasn't bad. Okay. Why do you think, with you guys being in honors, I would give you a first example of factoring like the one on the board? Why do you think, with you guys being in honors, I would give you the first example of the one on the board? How easy is that guy? Not very easy, but why not? What makes him hard? Sorry. Mission trips, they go into accents. It just comes back every now and then. Katrina Kevorkian and Maggie Corey, they just speak British all the time. Coming back. Or maybe they are. Coming back. What makes this difficult? Number in front. And I think last year that's when you needed the modified x method, right? So is this easy? No. How do you do it? Let's go over to the sideboard. It's up to you. If you want to just pay attention to all three and be like, I don't like the first, I don't like the third, I'm only going to do the second, fine. If you're like, wait, the first can go faster if I become a master at it, I like going faster. Maybe I'll try to practice with the first method. Or maybe the third one, it's shorter than the second one, I think, so maybe I'll try to get that one down a little bit. Anyway, I'm going to show them to you, each of the three, just so that you can know what I'm doing in class sometimes when I go quickly as we move on in the year. Right now, I'll show work, and that's okay. But you guys can also, hopefully, tell me what your preferred method is. I'm going to guess it's the middle, but just in case, I'll show all three. Okay? Guess and check. Guess and check says take that function, 3x squared plus x minus 10. I'm going to go ahead and write it. Just because in all of these, we do have to think about our function itself. Minus x? No, plus x. That was almost dangerous. Minus 10. The guess and check method said, hey, guess what? I know what the answer is supposed to look like. Whenever we factor a trinomial, the answer is going to have two binomials being multiplied. Okay? And the guess and check is also going to where this answer came from. It's going to know that when you FOIL a binomial, the first times the first, f, is always going to get you this first term, as long as it's written in descending order is what we call it. The outer and the inner, an x term and an x term, are going to combine to make the middle. And then the last times the last is going to always give us the last term. As long as you have an x plus and an x minus, even with a number in front, I know that the first two, this little f, has to result in 3x squared. Now hold on. If f has to result in 3x squared, what x term times what x term would give us 3x squared? 3 and 1. That's all we got. 1 and 3, 3 and 1. So I'm going to go ahead and say, all right, I know that 3x and x make x, I apologize, 3x squared. Now, in FOILing, what would you do next? Usually, outer than inner, right? But we're not going to do that when I'm doing the guess and check method of factoring. Instead, I'm going to go over here and look at the L. And I'm going to say, okay, so the f, 3x and x gets me 3x squared. The L needs to get me 10. How can I get 10? 2 and 5 or 1 and 10. Those are my options, right? 2 and 5 or 1 and 10. So I'm going to go ahead and ultimately think about all the different possible combinations. Now, just because I know how to do guess and check, I do this in my head, like mental math going through until I find the right ones. What I'm trying to look at is, for instance, if I was to do 1 and 10 right now, not even worrying about the positives or negatives, just 1 and 10. How do I check to see if this is right? The first works. The last works, except for the sign, which we'll figure out in a second. But what doesn't work? Why is this a wrong answer? We have to check the outer and the inner. What would the outer be? What would the inner be? 30 and 1 will never make 1. They'll either make 31 or 29, right? So 1 and 10, not so good. Can anybody like mental math it and look ahead? What if I was to switch the 1 and the 10? Because of this number in front, it's going to be different. If I switch, is it any better? Some of you already can tell, no, maybe you should be doing guess and check if you can do that mental math. 3 and 10 make 7 or 13, not 1. So is 1 and 10 a good combination? So what's the only other combination for us to even think about? 2 and 5 or 5 and 2. Now some of you are already mental math playing with it and hopefully already found the right one. But what if I was to do 5 here and 2 here? Why is that bad? 15 and 2? No. But why is the other one so great? Did anybody already beat me to why it should be 5 and 2? 6 and 5. Makes 11. Oh, or 1. Now hold on. I need a positive 1. So is the 6x going to be positive or the 5x? 6x. So I'm going to put a plus there and I'm going to put a minus there. Not only do I have the right answer, but I also FOILed to make sure it works. I guessed and checked without really showing much work. It's easier if you can get the mental math down. It's harder if you tend just to kind of make a jump and be like, meh, I think it's right, and go. Oh, it's going to be real bad if you do that. Okay? So, is this good? If your mind can do it, yes, it'll help you go so much faster. You don't even have to show these arrows once you get used to it. But is it dangerous? So dangerous. Because some of you have gotten really, 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 really used to the ones without numbers in front, just kind of throwing things in and being like, I think it looks right, and move on. You don't actually check the foiling. Whether or not you write it, you don't even mentally check the foiling, and you can get it wrong quite frequently. Now the X method, we're going to come back to in just 1 second. He's the one that most of you guys are more familiar with. Let's go to the table method real quick. The table method, there are different table methods, just to be honest. The one that I know of basically does guess and check, but it shows work. It basically does guess and check, but it shows work. So what it does is it says, hey, let's take the function, which is plus x minus 10. Let's take the 3x squared. Let's take the negative 10. And let's think about all the different possible combinations. You don't even technically need to draw that little line. But you can put that little plus x in the middle. The idea of the table method is saying, okay, what are the different ways that I could get 3x squared technically? You could say, okay, 3x and x. Could you also do x and 3x? Yeah. those can be flipped either order. So a 3x and an x, that's what I know. What are the different ways that we can do 10? 5 and 2, you already know what the answer is, true. Let's do 1 and 10 first. Let's just say you were writing it out, okay? Let's say you chose 1 and 10. Do you guys notice that if or when we had 3x with a 1 and x with a 10, did you notice that the outsides multiplied and the insides multiplied? So what you can do is you can check and you can say, okay, that'd be 30x and that'd be 1x. Does 30x and 1x help us at all? No. Okay, forget him. So let's do our 3x and x, and let's instead do 10 and 1. 3x and 10x. Does that help us anymore? No. Okay, so that one didn't work. That one didn't work. 3x and x. How about 2 and 5? 6x and 5x. Ooh, I like that. I like that, right? We want the 6x to be negative. No, we want the 6x to be positive. We want the 5x to be negative. How do we do that? It gets a little bit harder. But you can put the plus, and you can put the minus. And then as we go, 3x minus 5, x plus 2, and we get the same answer over there. Now, in order to make this something where you kind of get into a rhythm, otherwise the signs can get a little bit messy. What you ultimately want to do is as you go down, the 6x would come down here, and as you go up, the 5x would go there. The 5x needs to be negative, the 6x needs to be positive. There's a way of like having the system, the sign will always be in the correct position. Kind of messy, unless you like the idea of the guess and check. The grouping always gets super confusing. You like the idea of just checking the different combinations of putting these different terms together until you find the right one. So then in each of these, if I was to follow the system, technically, as you go down, that would be down here. As you go, I forgot there was a point to the positions, my bad. As you go down, as you go up. And so you can make your signs based on the different terms that you have. But the negative 5x and the positive 6x will give me positive 1, 3x minus 5 times x plus 2, done. It's a way of showing work with the guess and check method. Okay, X method. Let's get to the one that you're familiar with. And we'll take a vote at the end just as far as what method you think you will probably try to use for right now. X method, take the function. It's technically the modified X method. Why? What do we put in the X over here? A times C, good. First times the last. So the first times the last, A times C is going to end up being negative 30, right? What do we put down here in the bottom? B. 1. What are we looking for side to side? Numbers that multiply up, right? Numbers that multiply up and add down. So is that multiply up and add down? Multiply up to be negative 30 and add down to be 1. Most of you pretty quickly would have figured out that those are going to be positive 6 and negative 5, right? I'm assuming. 6 times negative 5, got it. 6 minus 5, got it. But the struggle isn't so much in setting up the x, unless this number is really, really big. Then it's like, oh, divided by 1, divided by 2, divided by 3, divided by 4, and you have to keep on going. Some of you don't like mental math, so you escape that. But for the rest of you, oh well, just keep going and you'll eventually find the right pair. But what happens once we have these two? That's where people get confused. Grouping correctly, we can't even group until we take the middle term and say, hey, by the way, you came from what two guys? 6x and negative 5x. You have to take this middle term and break them apart and say, hey, by the way, you came from, oh look, you came from 6x and negative 5x. But the problem is just seeing the 6 and the negative 5, those aren't parts of the answer necessarily. I mean, they need to come from the factors in some way, shape, or form, but the 6 is not in one of these spots. He's not anywhere. He only happens when you multiply the first times the last. So what we have to do is bring down the 3x squared. Now we have 4 terms. And why does it say X method with grouping? X method, figure out the 6 and the negative 5. Figure out where the middle term came from. Write down, everybody, what's grouping? How do we group? Oops. The first two, group the last two. You guys notice I didn't do minus, I did plus and negative. Helps you avoid so many mistakes. When you pull out a 3x, what's in common? Most of us are pretty good from here on out. When we pull out a negative 5 or a plus a negative 5, what's in common? Or what's left, I should say. X plus 2 and x plus 2. We pulled out the negative from both binomials. And then what's left for us to do? See that those two are in common. Pull the x plus 2 out. And what's left behind when x plus 2 gets taken away? 3x minus 5. Did it end up being the exact same answer as the guess and check method? Yeah. Could you still check it and make sure you're right? Yeah. What's the safest way to check? FOIL it. Did it ultimately turn out to be the same thing that we would have gotten if we had just rewritten this to be 3x minus 5? Now guys, these are just some ways. There are 3 ways. There are tons more on the internet if you were to look, because any kid in the American school system has to at least get through Algebra 1, and every Algebra 1 class has factoring. You're in pre-cal, you've been through Algebra 2, you have to have a way that works for you. Some of you are going to practice one of the other ones because you're like, I think I might like it. But for right now, if you were taking a quiz or a test today and you had to do a factoring problem, how many of you, to be safer rather than sorry, would choose guess and check? How many of you guys would choose the X method? How many of you guys would choose the table method? Okay. So the majority of you are going to choose the X method, so I'll normally do that. But just in my head, I'm almost always guessing and checking first to make sure we get the right answer. Austin.
Would the answer be x plus 2 and 3x minus 5 or the fraction?
Ah. We were just doing the factoring. So let's take all of that work and let's come over here. And let's go ahead and say, okay, hold on. So far, why is Austin asking what he's asking? Why is he asking what he's asking? The whole point of this was to find the zeros, and the zeros say set f of x equal to 0, right? And so far, what's the only thing we've actually done, even though it took a lot of work shown 3 different ways? Didn't we just figure out this is 3x minus 5 times x plus 2? Are we done? No. But we do have the factoring, right? So how do we finish the problem? If we have factors equal to 0, why did I say factor, 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 factor? Because it's always the same final step when you factor. Factors equal to 0, set each. What are they called? They are binomials. Set each factor, though. When you factor, set each factor, what? Equal to 0. To have a multiplication to be 0, either this guy is going to be 0 or that guy is going to be 0. So we have 3x minus 5. I know some of you guys can do this mental math. So can I. I'm trying to show the work. X is equal to, add the 5, divide by 3. Got it. X is equal to negative 2. Got it. At some point during the year, we'll talk about extraneous solutions where the math says, yay, he's right, but plug him in. Domain restrictions might say he's wrong. But for right now, this polynomial domain is all real numbers. No stress about any of these being illegal. The zeros of the function are negative 2 and 5/3. How do we get them? Factor. If we were to graph this function, this is this function, just a graph. If you want to do a quick sketch, this is what he looks like. He ends up being a parabola that's been shifted down. I think it's negative 10. Yeah, plug in 0. His y-intercept is negative 10. He has zeros at negative 2, which we found, and at 5/3, which we found. So if you did have a graph, like we saw in the graphing calculator handbook, you could find the zeros just by looking at the graph or by using the function in your calculator. But when I say zeros, what I'm talking about are x-intercepts, not the y's. Okay. But even though I probably should have written it up there, factoring is a big idea of today. Technically, in context of our section, technically the bigger idea is graph behavior. Technically the bigger idea is graph behavior. So I'm going to come back here, and as you guys are starting to sketch down, or I should say write down, increasing, decreasing. Technically a big idea before we ever got to graph behavior today was factoring. Reviewing and using it. Technically it was for zeros. So it was for a graph characteristic. Factoring to find zeros. Then we're going to finish with graph behavior. See, now you guys wish it was cold, huh? Now it's kind of like hot and stuffy in here. Ugh. What's a quantity that increases and decreases? What's a quantity that increases or decreases? There are like infinitely many answers. There's so many things that increase and decrease. What's something that increases and decreases? Time! No. Time doesn't increase and decrease. Time just keeps going. Temperature, right? Because a lot of you came in and you were like, oh, it's cold. It went down. But then what did the temperature do as time passed? Without the air on, yeah, it went up. We live in San Fernando Valley. We're almost through the summer in a sense of like temperature-wise. Temperature increases and decreases. What else increases and decreases? No? Well, lifespan, if you're thinking about like population and how long people are living, yeah, that could increase, decrease, depending on what's going on. The olden days, lifespan was getting like shorter and shorter because of all sorts of diseases and all sorts of things like that. As technology and we can even think like the Reformation started a lot of things. But as like there were advances in medicine and lifespan started to increase, right? Fast food and all this, that, and the other, a whole lot more preservatives and all this weird stuff that we're ingesting, or even maybe like smog and pollution from all of the nice techie things that we had. Cancer started maybe, we're kind of, so yeah, there is an idea of maybe increasing, decreasing. I was thinking like stocks. Aren't they constantly increasing and decreasing? Right? That's a people that make like millions of dollars off doing penny stocks, like they're constantly always making all these trades and it's craziness. Super risky. But anyway, talk about your parents and their retirement funds. Anyway, so let's do it with the stock market. Increasing and decreasing. The idea is, okay, going up, going down, we got that, right? And if you were to look at this graph, and if I was to say, where is it increasing, where is it decreasing? Some of you would be like, oh, it's super obvious. It's decreasing on this branch. It's constant on that branch. It's increasing on that branch. But here's one thing that if you don't have as your foundation, or if you don't have as like your construct that you're thinking about, you might get reading graph, just like you read a book in English. Maybe not in some other languages, but in English we read from left to right. So that's how we're reading graphs also. But that's actually hopefully kind of making sense, because what we're doing is having the x just kind of naturally go their direction from negatives to positives. And as we move from left to right, what are the y's doing? So increasing or decreasing describes the function behavior. Why am I trying to make the function behavior? Because then that means the y behavior. Remember, function value, y values. Zeros of a function, y's are equal to 0. Increasing, decreasing, y behavior. The heights are falling or the heights are rising. That's why I have rising and falling. So the y's are going up, aka the function is rising, or the y's are going down, aka the function's falling. So the increasing and decreasing is actually probably, hopefully, pretty easy. But then you get to questions like this where it's like, hey, let's give you functions and let's ask you, where is it increasing? Where is it decreasing? And guess what? We just reviewed yesterday, right towards the end, what kind of notation? Right before that? Sorry. For domain, for range. And now for increasing and decreasing, we're going to be using interval notation to describe the where. Because increasing and decreasing isn't at x equals 1 or 2 or 3 values. Increasing or decreasing is going to be over whole intervals. So let me go ahead and zoom in on this example right here. Using interval notation, and specifically, just to help you guys out, the where, if I were you, as you're writing down the example, summarizing the directions just like we do in homework, the where, what I mean is the x intervals. I'm not going to call that domain, because domain is specifically talking about the x's for the entire function, all the x's that work. For these, it's all the x's where a certain characteristic is true. And we're just going to work together on these, because the more examples that we can do, and the more I can kind of talk them through, then the more capable you'll be in homework when you are individually practicing and seeing how you can apply it on your own. So looking at this first function, can you guys see it? It's light blue. Let me go ahead and turn off the second light so it's a little bit better. Looking at this function, light blue, f of x equals x cubed. Here's the basic graph. Where is the function? For what x interval is the function increasing? You would write x is within. I'll just start with increasing. For what interval is the function increasing? So if I were you, I would pick a point on the graph. I would go as far left as you possibly can, and then start reading the graph. What happens to that point? It starts to go up. And if it's going up, then what's happening to the y's? Increasing. Good. So for what x values? Well, hold on. If I was to keep going left and then move left to right, isn't it always keep going left and move left to right? Isn't it always? What's it always doing? No. You're picking an earlier starting point to think about the behavior. But you always have to move left to right. So as I pick an earlier and earlier starting point, what's the function still always doing once I start moving left to right? Yeah. So how far left can I go to start where it will be increasing as I move left to right? Yeah. Infinity to the left, though, is specifically what kind of infinity? Good. Oops, wrong one. Wrong one. Struggle. So if you could keep on going left, keep on going left, keep on going left, keep on going left to start reading left to right, you'll always start increasing wherever you or however left you go. So from negative infinity, this thing is increasing. It's going up. And then how long does it keep increasing? It's going to keep on increasing to infinity. Now, just a few of you are wondering what's going on at 0. Just a few of you are wondering what's going on at 0. Because it does start increasing slower and slower and slower and slower and slower. But since it doesn't actually level off for a time, we don't say it's constant. At 0 itself is an infinitesimally, well, basically it has no distance in and of itself. So we don't say that it stops increasing. It doesn't truly stop increasing and start going constant anywhere. It just increases slower, 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 and then it starts increasing some more. So we go ahead, since it's just a point where it goes flat, it's just a point, and it's not like a whole interval like that guy. We don't even split it up. But here's the bigger question. Where is it decreasing? As you go left to right, is it decreasing for any part of it at all? No. So none. Not every graph decreases. Now this one's a little bit nicer because it does have different things that it's doing. So first of all, how many branches of this will be increasing? How many branches will be decreasing? Good. So let's go ahead and do the 1 first because we just did 1 interval here. Let's do another 1 interval. Then we'll figure out how to do the 2. So where is this function decreasing? It's decreasing from the point -1, 2 to the point 1, -2. But remember, we're just trying to talk about who? The x intervals for the where. The y's, that's what's going on when we say the word decreasing. So we're not saying the y's are decreasing from 2 to -2. We're saying where they're decreasing. And they're going to be decreasing for all the x values between -1 and 1. All the x values between -1 and 1. Now we don't do closed intervals because technically at -1 it's a transition from increasing to decreasing. So we don't say he's in either camp. We just keep him totally open. We keep the intervals totally open, and he's just going to be like a separator, like an in-between. Technically he's called like a critical number, but that's for calculus. Okay, increasing. Increasing. How left can you go of this increasing branch? How left can you go? Yeah, but infinity that way, good. So from -infinity, but hold on, it stops increasing at what x value? At -1. It stops increasing at -1. And the book might go ahead and put like a little U, a union symbol for or, which is okay. You could also put a little comma, just like you're used to doing when you have separate answers, to say, hey, and this is also an answer. You could put a comma also. But there is one other part of the graph where there's a left and there's a right to another increasing branch. 1 is the x value where it starts to increase again until what x value? To infinity. Got it. So let's go to the last one. You can separate with a comma or you can separate with a U, which is a snazzy term, union. It just means or, basically. Okay. Where's this function increasing? X interval. I'm going to write down what Robert said. If you agree with that, raise your hand. I see Aiden, I see Kyle. Austin agrees. Sam thinks yes. Gavin's just throwing in his hat saying, I think they're right. Okay, let's talk about it then. Increasing, moving left to right. Do you guys see that this branch is increasing? Does that make sense? It's going up. But, question, how far left could you go and it's still going to be uphill? Well, these graphs go on forever. So this is going to be uphill forever, but forever in what direction? So for all the x's to -infinity on the number line, if we were to keep on going, make more x's, keep on going and make more x's, and keep on going and make more x's, -infinity, all the way up until what x value, at what x tick mark does it stop? 0. It stops at the 0 x tick mark. Now what's going on from 0? Well, hold on. When does it change behavior again? Okay. So between 0 and 2, Robert just said constant. Do you guys agree? Because it's not going up or down. So yes, there is an interval where this function is constant between 0 and 2. And then hold on, what starts happening at the 2 tick mark? For all these x's, all these points, they're going to be down, decreasing. Yes. Yes. Are we practicing with interval notation? Yes, but are we applying it to talking about and describing how graphs move and change and behave? Yeah. So whenever you're thinking increasing or decreasing, you're looking at whether the graph is rising or falling, but you have to read the graph the correct way. And the correct way to read a graph is to go from left to right. Okay? So you have to think we're always moving from west to east to the other direction. Because what's uphill for this guy would be downhill for someone going the wrong way, but they'll be going the wrong way. So always going left to right, okay? Let's keep going. Average rate of change. Ugh. What? How does this fit under graph behavior? Well, we were just talking about graphs going up and going down. So maybe it makes sense that we'll talk about how fast they're going up and how fast they're going down. And how fast, that has to do with rate. But the nice thing is, even from, what homework was this? Oh, no, it wasn't you guys. It was Calc AB, I think. Never mind. They should have remembered it from pre-cal, but they didn't. Rate of change has to do with slope. Rate of change has to do with slope. And this should make sense to you guys, because if you're thinking about a graph going up and a graph going down in the sense of increasing and decreasing, it makes more sense probably to most of you on a downhill. The steeper the slope, what's true about the speed that you'll go, right? The steeper the slope, the faster you'll go, right? Now, for some of you, that's hard, because then it's like the steeper the slope the other direction, if you're going uphill, well, the slower you'll go. Well, the struggle is we're not really talking about you, an actual person, like walking this thing. We're not really talking about you on a skateboard trying to go uphill. No, that's not the point. The point is just trying to illustrate the fact that the steeper the graph, the faster the rate. And the rate could be an increasing rate or the rate could be a decreasing rate. And all of this can be seen steepness by the slope. Haven't we already talked about the slope formula? What's different though? How is this different than the other one that we used? Oh, but y is really just what kinds of values? Okay, so it's really just y2 minus y1 over x2 minus x1. Change in y over change in x, we just use that nifty triangle, the delta symbol that means the same thing. Ooh, but who's this guy? This is new, right? M we know, because M just stands for what? But what's SEC? Well, hold on, look down here. You saw it in geometry, because these were the guys who could cut through circles instead of having to skim the circles. You just haven't seen it cutting through, probably, many other graphs since geometry. But the truth is, a secant line can cut through anything, and does cut through anything. So when M secant is up here, that just means the slope of a secant line. And we'll see where tangents come, but not yet. Not now. That's actually where calculus comes from in some ways. The tangent line's way harder. Secant line's not too hard at all because it cuts through. What does it have to at least include on the graph? 2 points. And what can you do with 2 points? Find a slope. Oh, nice. So if I have 2 points, I can find a slope, and if I can find a slope of that secant line, the one that cuts through, I can have an average rate. What's the average slope this entire time? Now, sometimes was it steeper? Yeah. Sometimes was it not so steep? Sometimes was it nice and downhill? Yeah, but on average, what was the steepness, or what was the slope on the entire interval? Now, sadly, with pre-cal, and especially with our abilities now, we can't really talk about the instantaneous slopes, like how steep was it there, or there, or there, or there, or there. Because it wouldn't have 2 points, it would only have 1. But we can talk about the average by just solving that formula. So, if they give us something like this, they give us a function. I think some of you might not have been done writing. Let me dual page it. Is that okay? You can actually see the function, the one that I circled in red. You can see it in the problem itself because it says f of x is equal to x cubed minus 3x. And then it says find the average rate of change. Now, guys, the words are going to look super complicated, but as you summarize the direction, find average, AVG, right? Rate of change. Given f of x is x cubed to 3x minus 3x. All they're saying is find the slope between these two. Oh, wait a minute. Where are my points? They only gave me x values. I want x's and y's, don't you? It's not a big deal. If you have the x's, what can you do with this guy? Plug it in, plug it in. Can't you use the x's to get the y's? Now, if you had a graph, yeah, I guess you could go pointing at stuff and then finding it. But remember, the dilemma is you're not supposed to be like going to your graphing calculator every 2 seconds. Not that you can't ever, but you're not supposed to be. Needing to. We're in pre-cal. We're supposed to be able to do this without it. Or know how to do it, so maybe we can program those things one day. And make them do it for us. Dangerous though. But then coming back. Can't this formula be kind of cool? Hey, you don't actually need the y's. All you need are the x's. And with our cool function notation that we've been practicing, we can go get the y's ourselves and then be able to use it. So f of x2 minus f of x1 all over x2 minus x1. That's going to get us our y2 minus y1 over x2 minus x1, but we're just going to have to work a little bit for it if we don't have a graph or if we're not supposed to be going to our calculator. So then we can come up here and say, okay, well, hold on. We're going to need to know who is f of negative 1, who is f of negative 2. Who else are we going to need to know? 0, right? So you could go off to the side and do this work and not have to, like, put these equations in and have this nasty thing like the difference quotient that you have to do all this work to. Maybe it's nicer to do it off to the side. And if you do negative 1 cubed, oh dear, negative 1 cubed minus 3 times negative 1, wouldn't that be negative 1 plus 3? Yes. And negative 1 plus 3 would be 2. And then negative 2 cubed minus 3 times negative 2 would be negative 8 plus 6. Negative 2. If I plug in 0, oh, he's nice. Plug in 0, which is 0, right? And plug in 1, well, 1 cubed minus 3 times 1, isn't that just negative 2 again? Now, if you had a graph, you could see the negative 2, the positive 2 at negative 1, the 0 at 0, the negative 2 at 1. If we have these values, it's not going to be that hard to plug in because all we have to do is say, okay, hold on, what's going on at negative 1? I have 2. What's going on at negative 2? I have negative 2. There's my y2 minus y1. And I end up with my average rate being 4 over 1 is 4, right? And if I was to label it, it would be units of y over units in x, like we did in calculator worksheet number 2, where it was like pounds per month or year or something. What would I do differently for letter B? Well, if it just tells me from 0 to 1, won't I just change my formula? And instead of f of this guy, it's going to be f of 1. Besides f of that guy, f of 0, and 1 minus 0. And just to make it quick, we've already plugged in the f values. We go find the y at 1, go find the y at 0, and we already have them. The y at 1 is negative 2. The y at 0 is 0. And if you guys notice, if we were to come over here, it makes sense that this one between these two would be a really steep, as shown by a positive number slope, positive slope, and this one would be a, oh dear, there we go, would be a negative slope. So the picture should make sense with it too if you're able to compare. Average rate is talking about slope. Okay, there's one last characteristic that we're going to talk about. If you guys look at the backboard, our quiz has been moved to Tuesday, that way tomorrow we can go over homework and see what questions you have. It's going to be too much to try to fit in the quiz tomorrow as well. Struggle with the 3-day weekend, but we can do it. I want you guys just to write in these little tricks. We've actually already talked about these because this is just y-axis symmetry, and this is x-axis symmetry. Sorry, origin symmetry, my bad. But there's a new way of testing. And the new way of testing has you guys playing around with plugging in a negative x and seeing if it stays the same, kind of like we did with points, but now using functions, or plugging in negative x and seeing that everything becomes the opposite. Let me see what you guys can do with even and odd over the weekend. Using examples, not over the weekend, tonight, sorry. Using examples. Tomorrow we're going to go over homework questions. So I realize you might have a couple holes in this homework because we didn't get to practice even and odd. Oh, I took those ones out of the homework. Those ones aren't even in there. If they are, I'll put a quick comment on the assignment. I don't want you guys doing anything that looks like that. I wanted to show that to you. We didn't get to do examples on even and odd. Let's see what you can do. Try one, try two. And if you need to stop at the very end of homework, put little question marks. We'll talk about it tomorrow. Bye, guys. Quiz not until next Tuesday. Tomorrow will be troubleshooting section 1.5, making sure we're okay. And reviewing a little bit. There we go. Jason, come here for a second.